Okay, so standard electrode potentials. The standard electrode potential for an electrochemical cell is going to depend on the two specific half reactions that are involved. And it's a measure of the potential energy difference between the two electrodes. So we can think of each electrode, each half cell, as having its own potential. And that's called the standard electrode potential. Then the standard E cell is going to be the difference between those. So it's a little bit like water and a change in elevation, right? So maybe we've got something up here and something down here, and we've got a tube or something, and the water's going down. How fast the water goes is going to depend on the difference in height, the difference in potential energy of those two places, right? So E cell here measures the difference between the two electrode potentials. It's the potential energy difference. Yeah, see, I drew a picture that here is on the next slide. So this has high potential energy, this has low potential energy, and so the water's going to flow from high to low. When our two half cells are connected, the electrons will flow from the electrode with more negative charge. That has greater potential energy. Remember, the more negative it is, the more the electrons want to get away from it, right? They're going to flow from the more negative one to the one with a more positive charge. It may have a positive charge, the electrons are attracted to the positive charge, or it may just be less negative. And the electrons are like, well, this is really negative over here, this is very repulsive to me, I'm going to go over to the other side, it's still negative over there, but not as bad, right? Well, the electrode potential in a single half cell can't be measured directly. And there's lots of different things in science that can't be measured directly. So we choose a point of reference. We do that with altitude. We've chosen to measure relative to sea level, right? We did that with heats of formation and standard entropies and other things. So here we assign a potential of 0 to a particular kind of half cell, and we say, okay, this is our standard, this is 0. We're going to measure everything relative to that. And so the 0 is called the standard hydrogen electrode, often referred to as SHE, she. And here is standard hydrogen electrode. We've got platinum in here in a solution of 1 molar acid, and we've got hydrogen gas up here, and the hydrogen gas is at 1 atmosphere. So those are standard conditions, 1 molar for solutions, 1 atmosphere for gases. The reaction that's happening here is 2 hydrogen ions will gain 2 electrons and form 1 hydrogen molecule. And this is reduction is gain. This is a reduction reaction, so this is going to be happening at the cathode, and we arbitrarily assign that to be 0. We're going to measure everything relative to that. So here we have our zinc cell, zinc anode, zinc ions in here, and we've learned that zinc likes to be oxidized. It'll lose its electrons pretty easily. So this is oxidation, this is going to be the anode. Now over here, instead of the copper or something else, we're going to put our standard hydrogen electrode. And we're going to use a voltmeter to measure the difference in potential energy between these two cells. So we have oxidation occurring at the anode, reduction occurring at the cathode. And we're going to define E cell as the difference in voltage between the final state and the initial state. So the cell potential is the final minus the initial. It's the standard potential of the cathode minus the standard potential of the anode. So that follows some patterns that we're familiar with. We take the final minus the initial. It's helpful if you always draw your electrochemical cells with the anode on the left and the cathode on the right, so that the current is flowing to the right, and that helps us to remember that the anode is the beginning and the cathode is the end. I guess it's alphabetical too. So the measured potential there is positive 0.76. If you missed that, that's up here on the little voltmeter. So by measuring the cell potential there, we can figure out the electrode potential for the zinc half cell, the anode, because we know what the cathode is. The cathode is 0. So we measure the potential of the cell is plus 0.76. The cathode is 0, and so that leaves the electrode potential for the anode. And so just simple subtracting, we get E for the anode is minus 0.76. We can look at an energy diagram for this and see that potential energy going up. The anode, the zinc, has a higher, a more negative, that's confusing, potential energy, and so the electrons will flow from the anode to the cathode like water going down a hill. This is a spontaneous reaction. The more negative electrode potential means greater potential energy of an electron at that electrode because negative charge repels electrons. So this anode has a negative 0.76 potential that repels electrons towards the 0 cell potential of the standard hydrogen electrode. If we use a copper electrode in a copper solution and use the same setup, then we're going to measure the cell potential to be minus 0.34 volts instead of plus 0.76 volts. So this tells us that this copper half cell has a more positive potential than the standard hydrogen electron. So it has lower potential energy for an electron, and so because the anode is at a more positive voltage, the electrons will not flow to the cathode. They're actually going to flow in the opposite direction. So the copper half cell has a more positive potential, which is lower. So confusing, I know. This one is higher. Remember that electrons are moving away from negative towards positive, and so the electrons want to move from 0 to plus 0.34. So they're wanting to go this way, and it's going to be non-spontaneous to go the other way. The more positive the electrode potential, the lower the potential energy of an electron at that electrode. Positive charges attract electrons. So that copper electrode is positive relative to the standard hydrogen electrode. It's going to draw electrons away from the SHE. The zinc was negative relative to the SHE, and that will tend to repel electrons toward the SHE. So that's how we define standard electrode potentials. You literally hook up cells to a standard hydrogen electrode and you measure the difference. By convention, all of these standard electrode potentials are written for reduction half reactions. Don't ask me why, but they just are. So for the copper electrode, the reaction that occurs there, copper plus 2 electrons to make copper metal, so copper ions to copper metal. That is a reduction reaction. The reduction reaction would have a potential of 0.34 volts. For zinc, also written as a reduction, zinc ion going to 2 electrons, plus 2 electrons, forming solid zinc. Here, that cell potential is negative 7.6 volts. And so this negative potential tells me that this zinc electrode is actually going to want to lose electrons. So they're going to run away from it. Electrons are going to go towards this positive cell. So here are my thoughts on the matter. So the book uses standard cell potential is equal to the electrode potential for the cathode minus the electrode potential for the anode. And if you're going to use that equation, which is what the book uses, then you just use the cell potentials listed for reduction reactions in the table in the textbook. I personally find that very, very confusing, and I get things backwards a lot. So what I like to do, because this matches up with other things that we've already learned, specifically with enthalpies of reaction, we can also write the half reactions that are happening and add the cell potentials. So if I'm going to write one of these reactions opposite, if I'm going to reverse the direction, make it an oxidation, then I'm going to change the sign on E. So for this zinc reaction, the zinc was actually losing electrons, and so it was going like this, right? Oxidation at the anode plus 2 electrons. So I've taken this equation and I've reversed the direction. So the standard potential for that is opposite in sign. And then if I want to know the standard cell potential, this is zinc plus 2 hydrogen ions going to zinc ion plus hydrogen gas. I'm going to take these two and add them together. So 0 and 0.76, 0.76. To calculate that this way, I need to identify which of these is the cathode and which is the anode. It turns out that this is, I'll do this in a different color. This is the cathode reaction, and this is the anode reaction. And so, not delta, so used to delta. It's the cathode minus the anode, so it's 0 volts minus negative 0.76 volts, which is plus 0.76 volts. I'm getting the same answer. I'm thinking about it differently. Anybody have any thoughts? Important thing to note here, you do not multiply the cell potential by a coefficient. So if this is multiplied by 2 or 3 or whatever, the cell potential is not multiplied. It's an intensive property. It doesn't depend on how much there is. Okay, so Here's a partial list of reduction potentials. So these are all written as reduction reactions. So reduction is gain of electrons, so we've got something plus electrons to form something else, and here is the electrode potential, standard electrode potential. And they're listed in order, more positive to more negative. It doesn't all fit. Here's the rest of it. Can you hear the sirens? Yeah. I don't have trains though. I just have barking dogs and loud neighbor children and sirens. So here we have high tendency towards reduction. These are going to be reduced, but those are going to have a low tendency to oxidation. When we get to the bottom of the table, here we've got things like here's our friend zinc, right? Zinc likes to lose electrons, so here this reduction reaction is not going to happen very likely, but we've got a higher tendency towards oxidation. And kind of in the middle here is the standard hydrogen electrode. That's the reaction that occurs, and that one is 0 because we defined it to be 0. Okay, so to summarize, standard electrode potential of the standard hydrogen electrode is exactly 0. The electrode with greater tendency towards reduction is going to be positive relative to the standard hydrogen electrode. We're going to have E0 be larger than 0. If the electrode has a lesser tendency towards reduction, it's going to be negative. The cell potential is the difference between the electrode potentials of the cathode and the anode. So you take the cathode minus the anode. The cell potential is positive for spontaneous reactions. It's negative for non-spontaneous reactions. Okay, so let's try one. Use tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius. The equation is balanced. So we need to identify the two half reactions. We don't have to balance it, but we have to pull it apart into two half reactions. So I'm going to put that lead and this lead together. So we've got 3Pb2 plus is going to 3Pb. And then I've got the chromium, and the chromium ion is the other one. Now there's some electrons involved here, right? So this one has 3 electrons, nope, not 3, 6. 6 electrons. And I'm just doing that by charge balance. There's 0 charge over here, 2 times 3, positive 6 over here. So there must be 6 electrons for this to be balanced. And for the other reaction, it's also going to be 6 electrons, but they're going to be on the other side. So this is a species gaining electrons. So this is reduction. Reduction occurs at the cathode or the anode? Red Cat. There's actually a local high school, they're the Red Cats. So that's the cathode. This one down here is losing electrons. That's oxidation. That's occurring at the anode. So what we need are the standard electrode potentials for these two things. Well, We're going to go look them up. So we had, losing my mind. We had, it was chromium 3 to chromium, right? So that's negative 0.73. And then we have lead and lead-2 ion. Sometimes you have to look around a little bit. And there are some that look very similar, and so you have to watch out. Like with the chromium, there's 2 of them that are chromium 3 here. But that one's going to chromium 2 ion, and this one's going to the element. So I want this lead plus 2 electrons going to Pb, and that says it's minus 0.13. So those are the values from the table, right? And so if I want the standard cell potential, I'm going to take the cathode minus the anode. So this is my cathode. And then I'm going to subtract the anode. And it's a good idea to use a calculator for this. Negative 0.13 minus negative 0.73, and I get 0.6. Yes.
Just a quick question. I know we got the values from the chart, or from the slide previous.
Mm-hmm.
Is there a reason we don't multiply by the coefficients, like how led to the
Yes.
the plus 2 charge?
Yeah, there is a reason. We don't multiply because electrode potential is an intensive property. It doesn't depend on how much of the stuff you have. Okay. Something like enthalpy, heat of reaction, is an extensive property. It depends on how much you have. So if you have a little tiny electrode or a big giant electrode, the potential is the same. That's not the case if you're burning a little bit of gasoline or a lot of gasoline. Okay, so that's why we don't multiply. Okay, now I just want to show you how I think about this. So when I look in the table, I see, aside from the numbers here, it's just multiplied by 3, I see that I'm using this equation as written, right? Up here, I've got Pb2 plus electrons going to Pb. It's the same things on each side, and so I'm going to leave this alone. The chromium one, though, is, this is the standard reduction, but what I've got in mine is backwards, right? I've got this one written backwards. So then, in my mind, let's see, how... I'm going to write that as positive because I reversed the direction. And then, to get this, I didn't plan this out very well, can you tell? To get the overall, I'm just going to take this one and add it to that one. And I end up with the same. Here I'm subtracting a negative, here I'm adding a positive.
Okay, does it really matter which way we do it? Because if we look up in the table, we just the number out of there, it'll still give us the same answer no matter if we reverse it or not, right?
Well, the thing is, you have to identify which is the cathode and which is the anode. Because if you take the anode and subtract the cathode, you'll get negative 0.6, which is wrong. So that's what gets a little confusing. If you write the half reactions out and you identify what's happening, this is gaining, that's a reduction, this is happening at the cathode, that's oxidation, that's happening at the anode, and label everything, then you can use this equation and you'll be fine. What I like about my method is I actually don't have to think about that. I'm just going to look, I'm looking for this one, and I find it the same direction, so I keep the same sign as in the table. This one I'm using in the opposite direction, and so I'm going to use the opposite sign, and then I add them together. It's the same difference, it's just a different way of thinking about it. So the answer was 0.6. Here's a conceptual problem. An electrode has a negative electrode potential. Which statement is correct regarding the potential energy of an electron at this electrode? The electron here is going to have a lower potential energy than it has at a standard hydrogen electrode. It's going to have a higher potential energy than at a standard hydrogen electrode, or it's going to have the same potential energy. These are hard to think about. So here we have our SHE, and that's 0. This is telling us that this electrode has a negative potential. So our electrode is, negative 0.x volts. So an electron at this negative, actually I don't like the x. Let's say negative 0.5. It's making up a number. At this negative electrode, is a negative electron going to be attracted to this or repelled from it? Like charges repel, yeah? So this is has a negative potential. It's going to make the electrons want to go towards something more positive.
Would it be a higher potential since it's positive?
Electrons move from a high potential energy to a negative potential energy. High to low. It's very confusing because the plus and the minus seems to be backwards there. So at a negative electrode, the electrons want to leave. They want to go to something that's more positive. And then we think about water. Does water flow from a low place to a high place, or from a high place to a low place? It flows from high to low, right? So the electron's wanting to leave. It's wanting to go from this place to that place. That means that this is higher potential and this is lower potential. And that's so confusing that the person who wrote the slides published by the publisher has the wrong answer in their slides. It's right in the book, but the slides are wrong. Any questions?
So the answer is B, right?
The answer is B. This negative potential this electrode with a negative potential has a higher potential energy than the standard. The electrons are going to want to move away from this. They move from high energy to low energy. Okay. Predicting the spontaneous direction of a reaction. What we're going to do is we're going to look at the standard potential for each half reaction. The more negative one will tend to lose electrons. Losing electrons is oxidation. The more positive one tends to gain electrons, that's reduction. For this to be spontaneous, the cell potential has to be positive. So we can look at it that way. And that kind of goes along with this. Negative charge repels electrons because they're negatively charged. So electrons are going to move from the more negative to the more positive electrode. Oxidation is loss of electrons. Oxidation occurs at the anode. Something that is sometimes easier to think about is any reduction half reaction is spontaneous when paired with the reverse of a half reaction listed below it in the table. So if you identify the reduction half reaction, anything below it paired is going to be spontaneous, anything above is going to be non-spontaneous. So let's look at an example. Here we have nickel and manganese. These are both reduction reactions, gaining electrons, and these are the potentials from that table. And so we want to predict which direction are the electrons going to go. Well, which of these is more negative? This one, right? This is more negative. The electrons are going to leave the more negative one. So that tells me that manganese is over here as the anode. They're going to go towards the more positive one. So the nickel is over here. So the nickel is going to do a reduction. The manganese is actually doing an oxidation. Whoops. And what makes sense to me is I'm writing this equation backwards. I'm going to write the sign backwards. And then I'm going to add those together. Again, our brains are all mixed up with the positives and the negatives, so let's just use a calculator. So that's giving me a positive potential, which tells me that it is spontaneous. So with this as the anode and that as the cathode, the electrons are going to go in this direction. So using the book method, E cell equals the cathode potential minus the anode potential. Well, again, I can look at these and say, well, which one is more negative? This one's more negative. That means the electrons are leaving that one, right? Oxidation is loss of electrons. So this one is going to be an oxidation. This one's going to be a reduction. Reduction occurs at the cathode. Oxidation occurs at the anode. So the potential at the cathode is negative 0.23 volts, and I'm going to subtract the potential at the anode, which is 1.18 volts, and I'm going to get plus 0.95. Any preferences for which method makes more sense to you? I won't be offended.
I like your method better.
Thank you. Anybody like the other? It's okay. Well, I'm not getting any responses, so I'm going to go ahead doing it another way.
I feel like with yours, there's less to think about, because like it just makes sense if you use it in reverse and you just flip the sign. When you have to write out everything, it's just like you're like, okay, which one's the cathode again? Which one's the anode again? I feel like there's just too much to think about with that one.
Yeah, that's why I like it too. It builds on something we're already familiar with, and there's less thinking involved. And anytime there's less thinking involved, I think it's good. Thinking is good, but let's save it for times when we actually have to think. And somebody said he likes both, so okay. Okay, so this one is an example without calculating the cell potential. And so what I did here to prevent us from doing that is I put the part of the table we're going to need and I cut off the electrode potentials. Predict whether the redox reaction is spontaneous. And then we're going to draw a picture. So here, zinc and nickel, making zinc 2 plus and nickel. So I'm going to go ahead and do it my way. So what I've got here is I've got zinc going to zinc ion, and that would mean the electrons have to be over here. And then I've got nickel 2 plus, that must have electrons on this side, going to nickel. So I took this equation and I split it into two pieces. So here we can't calculate, but we can look at the table, and what we're looking for is these two half reactions. And okay, here's zinc. And here's nickel. So the spontaneous reaction would be the higher one going as written and the lower one going backwards. So is that what's happening here? Nickel plus 2 electrons. We want it that way, and here we want zinc going to zinc ion. This one's backwards, this one's forwards. That tells me this is spontaneous. Any questions? Again, with this, I kind of think about people, and it's a list of who gets to choose, who gets a preference. And so the person at the top of the list, or the higher in comparing the two things, gets to be the right direction as written. And the one underneath has to do it backwards. And when you got it set up like that, it's spontaneous. You can think of this guy as being stronger, I suppose. And so he's going to overpower this guy. The next part says, sketch the electrochemical cell in which the spontaneous reaction would occur. Label the anode on the left, the cathode, and the direction of electron flow. You should learn how to draw electrochemical cells. They do not have to be beautiful. So we've got 2 containers, 2 beakers. We need to put a salt bridge in here. And we've got liquid on both sides. We have some sort of a metal piece here. And then we're going to connect these by a wire. This is the anode, because the anode's always on the left, and the cathode is on the right. The anode is where the oxidation occurs. So if I look at these, oxidation is loss of electrons. The zinc is the one being oxidized. So that tells me that this is the zinc electrode here, and there are zinc ions in solution. This is the reduction. It's happening as given in the table. It's gaining electrons, and so that's happening over here at the cathode. Here we have a nickel electrode and nickel ions in the solution. The nickel is gaining electrons, the zinc is losing electrons. The electrons are going from the anode to the cathode. Is it spontaneous? Yes. Let's look at this one. Zinc metal with calcium ion, making zinc ion and calcium metal. Well, what's going on here? I've got zinc going to zinc ions. So for that to happen, I'm losing electrons. And I've got the calcium gaining electrons to make calcium metal. And then I'm going to look these up in my table. Calcium's here, and zinc is, where'd you go? Zinc's here. This will be spontaneous if zinc is doing this and calcium is doing the opposite. That would be spontaneous. Well, this is what's happening according to this redox equation here. Zinc is going to zinc ion. Okay, that's not what we're showing here. And calcium is doing this. The way the table works is if the higher one is going in the forward direction and it's paired with something below going in the opposite direction, it'll be spontaneous. But here I've got the opposite going on. This is not spontaneous. It's water flowing uphill. It's not going to happen. Here's a conceptual question. It's a thinker. A solution contains both sodium iodide and sodium bromide. Which oxidizing agent could you add to the solution to selectively oxidize iodide but not bromide? We need to look at this table, and we need to find the reaction. These are all reduction reactions. We're talking about oxidizing iodide. So we're going to find the reduction reaction and think about it as going in the other direction. All right, so here is iodide, and here is bromide. And these are going backwards. So these are backwards. That means anything above this going forwards would be spontaneous. Anything above with this. Anything above bromine here would be spontaneous with bromine and also with iodine. So if I want to oxidize the iodide and not the bromide, I need to pick one of these guys, because these will not oxidize bromide, but they will oxidize iodide. So it's multiple choice. So I have to look around. You have to look on this side. Whoops. We're looking on this side this time. And the only thing that shows up here is the nitrate ion there. So nitric acid will oxidize the iodide but not the bromide. So predicting whether a metal will dissolve in acid, most acids dissolve metals by reducing hydrogen ion into hydrogen gas, and then that's a reduction, and the oxidation will be the metal going to its ion. So here is a test tube with a coil of zinc in acid, and we see bubbles forming. The acid, hydronium ion or hydrogen ions, are being reduced to hydrogen gas, and the zinc is being oxidized to zinc ion. So this is a reduction reaction. So the metal has to be below on in the chart in order for this to occur. So metal whose reduction half reactions are listed below the reduction of hydrogen ion to hydrogen gas will dissolve in acids. There is a very important exception, and that is nitric acid. Nitric acid can oxidize metals such as copper that cannot be oxidized by other acids, and it does so using this kind of crazy reaction. This one is above the reduction of hydrogen ion in the table. So, yeah, the hydrogen ion one is actually the 0, right? So it's not shown here. Because it's on the next half of the table. Here they're asking which metal dissolves in nitric acid but not in hydrochloric acid. So this is the reaction that occurs for hydrochloric acid. And the nitric acid one is right here. So anything between these would react with nitric acid, but not with hydrochloric acid. So which one do you see in there?
Wouldn't we have to pick one above the nitric acid?
No, because the nitric acid is being reduced and the metal is being oxidized. So the metal has to be below. So here we've got silver. If we're just looking on this side, we see iron. We're like, oh, that's in there too. But over here, it's not this iron. Oops. It's not Fe, it's Fe 2+, and so that's not the same. And gold is way up here. Ooh, didn't mean to do that. Gold is way up here. And so gold doesn't dissolve in either acid. Oh, I forgot to do the answer on that one. So it was silver. And that's the end of that section, thank goodness.